Okay, everybody, so welcome back. I wanted to finish up a quick discussion of like some of these linear algebra, um, facts to kind of make it clear what it is I'm doing here in case you haven't seen this stuff before or in case it's been a while. Um, so I'd mentioned some of that stuff before. If you're confused about any of these matrix facts, so any confusion about matrices, I don't know why I capitalized confusion. So check the supplement. This is chapter 3 in the online notes section. Let me look at what section this is. Section 3. Yeah, so this is chapter 3, section 3. Okay, which will contain a lot of that stuff. Some of this stuff that I'm going to go over actually comes a little bit later, specifically for eigenmethods. I'm going to focus on one particular method for solving these systems, um, and well, okay, I will mention the others, but I'm going to focus on one particular one because it turns out that that one is the one that's going to get us basically everything that we need, and it's going to be the most useful going forward. So that's what I'm going to focus on. So then, um, what is it that I'm actually typically concerned with, right? My main concern in chapter 3. Now, this is not the only type of problem that we're going to be looking at in chapter 3. This is, typically we're going to be, so like in complete generality, we're going to be looking at some equations that are more general than what I'm about to write down, but this is definitely the meat of the chapter. This is the thing that is going to be our main focus in all of this stuff. So my main concern in chapter 3 are equations, or are systems of the form dx dt is equal to ax, okay, with initial condition like x of t sub I is equal to something I'm calling the initial vector x superscript I. Okay, so this is what I am concerned with. Now, what kind of thing is this in terms of the terminology that we adopted earlier? So that it's first order because the highest order derivative showing up is 1. It's just the first derivative. So this is a first order linear, right? So this is first order linear homogeneous because there's no f here system, right? So remember, technically, right, typically, what is this A? This A is some n by n matrix, okay, that can be written as, it has ij slots that look like this. Okay, so both I and j are between 1 and n. So the ijth entry is a sub ij. So this is my like general constant coefficient, of course, I should include here, right? The reason why you might say, well, that's a big thing to not include. This is all we're going to be considering in this chapter. So while a lot of this general theory can apply, like a lot of the statements I'm going to be making about these equations would apply to the variable coefficient case where this matrix A now, so the variable coefficients case is when A is some function of t, so that these component functions, these a sub ij's, would each be functions of t. You could talk about that in the general theory. A lot of the stuff follows, but we're typically not going to concern ourselves with that in this chapter. So you can just go ahead and assume that you're dealing with a constant coefficient thing here. Okay. Now, while everything I'm going to do is going to hold for a generic n by n matrix, most important case by far, and this is just due to, to keep the tedium down. So most important case is n equals 2. And this is similar to how we restricted ourselves to the order 2 case in chapter 2, right? Typically, like a lot of that stuff we were doing in chapter 2 works. It doesn't matter what the order of the differential equation is, but we did it for order 2 equations just because it made our life a lot easier. So anyway, that's the idea. That's the idea here. Okay. So typically, this A is going to be a 2 by 2 matrix. So what does that problem look like? What is it that I'm going to be looking at? So so then, if n is equal to 2, what does this equation look like? This is, dx dt is equal to a x, and I have some initial vector that I'm calling xi. Okay, well, if n is equal to 2, then my solution vector x of t is actually made up of components, call them x sub 1 and x sub 2 t. These are my components of my solution vector. A is a matrix A11, A12, A21, A22. Of course, if it's just 2 by 2, you can write this sometimes as, A, B, C, D, like you usually write 2 by 2 matrices. And then that initial, this initial vector, right? This is just me plugging in some initial time here and imposing this initial condition on it. So this is, since I know that this is x sub I, this is, x sub 1 of t sub I, x sub 2 of t sub I is equal to whatever this is. So if I call this like, x, I can call this like x sub 1 naught, x sub 2 naught. All right, we got subscripts and superscripts flying around, so that's what this is. Okay. All right, so this is generally what this thing looks like. If I actually wrote this out as not in this like truncated form, but if I wrote this this equation out in this way, this is a system, right? dx1 dt is equal to a. Well, let's do a little aside first, because this was one of the things that I didn't quite explain yesterday. If it's unclear to you or not fresh in your memory how matrix multiplication goes, let's do a quick aside here. How does matrix multiplication go? Matrix multiplication. Well, let's do this in a way that's kind of, let me do this in the least painful way to describe here. So if we're going to do that, we're going to discuss a few things first. Okay. So first, what does it mean to transpose a matrix? So if I have a matrix that's an m by n matrix, what does it mean to take that matrix and transpose it? To transpose, so this is the transpose of A. Well, all that transposing a matrix does is it swaps the roles of rows and columns. So what this is this is the matrix formed from A by swapping the roles of rows and columns. What does that mean? This means the ith row of a transpose is the ith column of A, and the jth column of A transpose is the jth row of A. Okay, so let's do an example real quick. So if I have a matrix, and let's say that it's 2, minus 1, 0, 4, 7, square root of pi, right? There's my matrix. What is A transpose? Well, A transpose is, so I look at the first row of A, that becomes the first column of A transpose. So the first column of A transpose is 2, minus 1, 0. And the second column of A transpose is the second row of A, so this is 4, 7, square root of pi. Okay. Another way of thinking about it is you take the first column of A, and that becomes the first row of A transpose. The second column of A becomes the second row of A transpose, and the third column of A becomes the third row of A transpose. So either way, you want to think about it, this is what you're doing. So notice this was a 2 by 3 matrix, right? Remember, m by n is rows by columns, so this is 2 rows, 3 columns. So that's a 2 by 3 matrix. So then A transpose is a 3 by 2 matrix, right? That's always going to work out like that. Okay, so what this means, if A and A transpose are going to have the same size, that means that A is going to have to be a square matrix. So instead of being m by n, it would be n by n. That's a square matrix. Okay. If a matrix is equal to its own transpose, that's called a symmetric matrix. A way of thinking about that is if you have a square matrix, there's what's called the diagonal of the matrix, right? Which is exactly what you think it is. That's the main diagonal. The other diagonal doesn't have a name, okay? So the from upper left to bottom right diagonal is called the diagonal of the matrix. You can think of transposing as flipping, right? Reflecting across the diagonal of the matrix. And so what's an example of a symmetric matrix? So let's do another quick example. Here's matrix A. Let's do it like this. Let's say this is 1, 2, minus 4. I'm going to fill this in as 4, 7. And I'm going to put 0 here. I'm going to put 0 here, 2 there, and minus 4 there. Okay. Notice that A is equal to A transpose. This is called being symmetric. When you form A transpose from this, the first row of A becomes the first column of A transpose. So 1, 2, minus 4 becomes the first column, which is 1, 2, minus 4, O. Second row, 2, 4, 0 becomes the second column, 2, 4, 0, O. Third row, minus 4, 0, 7. Third column, minus 4, 0, 7. So they're the same. All right, so this is the notion of transposing. Now, why did I want to introduce that? Well, notice that a particular type of matrix is a vector, right? So let's say I have the vector 1, 2, 3, and we think of vectors as column vectors. Now, that was a choice. There's nothing preventing us from thinking about vectors as row vectors instead. And in fact, if I take U and I transpose it, right? So this is a matrix, right? This is a 3 by 1 matrix. It's got 3 rows and 1 column. Okay, so a vector is just a type of matrix. So I know that most of you know that, but it's good to see this, over and over again, just to remind you, right? So if I transpose vector, what do I get? Well, that single column becomes the single row of this matrix. And so what I get is a row vector here, right? So I can think about this as a co-vector instead of a vector. There's this duality here, I guess you could think of, between vectors and co-vectors, or column vectors and row vectors. Okay, but the point is you can transpose a vector, you get a row vector like this. Okay, similarly, if you take a row vector, you can transpose it and you get a column vector, right? So similarly, if V is the row vector, say 3, 5, 7, then V transpose is the column vector 3, 5, 7. So the main purpose of this is if you have a row and for whatever reason you want to treat it as a vector, right? But of course you have built up vectors as all being column vectors. Well, then if you want to take that row and treat it along with a bunch of other vectors that are column vectors, then you transpose it. You can transpose it, and then it's a column vector, then you can do all the stuff you wanted to do with it. Of course, one thing you might notice here is, hey, I could have just transposed this again and went back to my original thing, which is also a fact that is true in general. What happens if you transpose the transpose of a matrix? That's just the matrix itself. Okay, it's just the matrix you started with. Makes sense. You swap the rows and columns, and then you swap the rows and columns again, right? So you're back to where you started. So this is what's going on there. Okay, all right. So let's talk about one other thing. Let's talk about something you know from Calc 3 or from 240 if you've had 240 or 461 before. The dot product of two vectors. If I have two vectors, u and v, right? So u and v in Rn. Now, when you were first introduced to dot product, you may have been thinking about these as ordered pairs, right? So maybe you're like, okay, u is the ordered pair u1, u2, and so on out to un, and v is the, sorry, not ordered pair, ordered n-tuple. V is the n-tuple v1, v2, all the way out to vn, right? And then you can define u dot v. This is one of the products of vectors you define, right? This is also called the scalar product, and the reason it's called that is because the result of a dot product of two vectors is a scalar, is just a real number. So to dot these two vectors, right, you would write this as u1 times v1 plus u2 times v2, and so on, all the way out to un times vn. This is a real number. So this is also called the scalar product, sometimes called the inner product. Okay, so this is a very, very important thing. This, you don't see it immediately, but this actually gives you the notion of length of a vector. So we can talk about the length of a vector. This gives us a notion of distance. Like I said, you may think the opposite. You may think that distance kind of makes the dot product work, but it's the other way around. It's the dot product that allows us to talk about distance and length. Now, you might say, well, okay, these are for ordered n-tuples, but like I can write u and v like that, but I could also write the u and v as column vectors, right? So if I have two column vectors, u and v, dotting them together is defined exactly in this way. Okay. All right, so that's how you dot two vectors together. Okay. Now, where am I going with this? All right, so let's do a quick example of dotting two vectors together. So let u be the vector 1, 2, 3. Let v be the vector -1, 0, 2. All right, then what is u dot v? Well, u dot v is 1 times -1 plus 2 times 0 plus 3 times 2. Now you might notice that there's some nice properties this dot product has. For instance, you know, it has the very nice property that it is commutative. So u dot v and v dot u are the same thing because multiplication of real numbers is commutative, right? So swapping the orders of u and v here would just be swapping the orders that I multiply these in, but that it doesn't matter. Okay, so then this is -1, this is plus 0, plus 6. All right, so this is 5. Okay. So then the dot product of those two vectors is 5. Now you might say, well, what does the dot product tell me? We won't get too far into that right there. You might remember there's this fact that the dot product's related both to distance, right? So, you know, the length of a vector, the length of u is, this is the length of u. You can take this as a definition. This also comes from the Pythagorean theorem or the distance formula. So this is the square root of u dotted with itself. So this is the square root of u1 squared plus u2 squared, and so on all the way out to un squared. All this is, of course, is the distance formula between the origin and a point u1 to un, right, an n-tuple in Rn. But this is how you get the length. This is a nice way of remembering it. It's just square root of u dotted with itself. Okay. There's also this fact that when you dot two vectors together, the result is the product of the lengths of the vectors times cosine of the angle between them, right, where theta is the angle between u and v. So you can prove this with just with some basic law of cosines stuff, just drawing the picture and using law of cosines for a triangle will make this work. Okay. Anyway, so this is, so dot product is related to length and it's related to the angle between vectors. That's kind of the geometric importance of it, which is to say that it is extremely geometrically important. In fact, it is the thing that makes Rn have the geometry that it does. That familiar Euclidean geometry comes from the dot product. Okay. All right. So, what am I doing? The original thing that I wanted to do was define matrix multiplication, right? So let's go back. Actually, no, I'm not going to go back yet. I'm now going to talk about matrix multiplication. Just to remind you how this works. So how does matrix multiplication work? Right, if I have two matrices A times B. First of all, the first thing you can remember is this is not even defined unless unless A and B are of the right size. So if A is an M by P matrix, B has to be a P by N matrix. So when you're multiplying two matrices, the order matters, okay? Because in fact, if you swap the order and these numbers don't work out, A times B could be perfectly fine, but B times A might not even be defined as a product. It might be literally impossible. So the number of columns of the first matrix has to match the number of rows in the second matrix. And the reason why this becomes clear if I write this as a matrix. This is an M by N matrix. So this is an M by N matrix. So if these P's match, the resulting matrix is M by N, where A is M by P, B is P by N. So those have to match, and then you get M's the number of rows and N's the number of columns here. What is this matrix? The ijth, so the ijth entry here So the ijth entry of AB is, we'll say A sub I as a vector transpose dotted with B sub j. What is that? Well, we're going to write A as a matrix made up of rows, right? So this is a matrix made up of rows. We'll call those rows A1, A2. So these are rows here. To A, how many rows do I have? M of those rows. Okay. And B is a matrix made up of columns. B1 is the first column. B2 is the second column. So normally we don't use this weird line thing that I'm doing here. I'm just doing this to show you how this works. And there's N of these columns. Okay. So what I do to multiply A times B is I look at the entries here. So what matrix do I get here? Let's start with the first entry here. This is the 1, 1 entry. I take the first row of A, I transpose it so that now it's a column vector, and I dot it with the first column of B. Now, if that is going to work, those vectors have to be of the same size. Well, how many components does the vector A1 have, this row? Because A has P columns, each row has P elements in it, right? P components. Similarly, because B has P rows, each column of B has P entries in it. And so P is equal to P, those things match up, and so I'm actually able to do this dot product. So what I would do is I would take A1, the row, and I would transpose it, and then dot it with the first column of B. That would be my first entry. A1 transpose dotted with B, or B1, sorry. If I'm looking at the entry in the first row, second column, I would take the first row of A, transpose it, and dot it with the second column of B. And I would continue doing that. First row of A dotted with the third column of B. And so on, all the way out to A1 transpose dotted with BN, right? And then I would do that here too. So in the second row, first column, I would take the second row of A, transpose it, and dot it with the, I would take, the second row of A, transpose it, and dot it with the first column of B. Right, and I would do that all the way down to AM transpose dotted with the first column of B. And I'd do this all the way over to AM transpose dotted with the nth column of B. Okay, so that is how you multiply a matrix. Let's do an example of this. One quick example, and then we're happy to move on. Okay, and so if A is the matrix like 2, minus 2, 1, 0, and B is the matrix 1, 2, 3, 4, or we'll do 2, 3, 4, 1, since I wrote 2 first. Okay, then what is A times B? So both of these are 2 by 2, so A times B and B times A are both defined. In general, it's not true that AB, right? So AB is not equal to BA typically. So this is usually your all's first run-in with an example of a product or a type of multiplication that's not commutative, right? Okay, what is A times B here? So this is going to be a 2 by 2 matrix, and it's going to be a 2 by 2 matrix that I form from these dot products, right? So let's see how this works. So I take the first row of A, think of transposing it. You can just kind of do that in your head, right? I think of transposing this, turning it into a column. The column is 2 minus 2 here. And then I dot it with the first column of B. So 2 times 2 plus minus 2 times 4. So this would be 2 times 2 plus minus 2 times 4. And that operation would be my first entry here. I should have given myself more room. Okay. In the first column, first row, second column slot, I would take the first row of A, 2 minus 2, transpose it, and dot it with the second column of B. So this would be, maybe I'll put an arrow here. This would be 2 times 3 plus minus 2 times 1. Okay. And this entry would be the second row, first column. So I'd take the second row of A and dot it with the first column of B. So this would be 1 times 2 plus 0 times 4. Okay. And then in this slot, this would be second row of A, second column of B. So this would be 1 times 3 plus 0 times 1. Right. So in all those instances when I was saying like first row times second column, the times I was using was not just normal multiplication, it's the dot product, right? That's what I meant. Okay. All right, so let's see. What matrix is this? Let's simplify this. So this is 4 plus minus 8, so that's minus 4. Here in this slot, this is 6 minus 2, so that's 4. Okay, this is 2 plus 0, so that's just 2. And this is 3 plus 0, so that's just 3. So A times B is minus 4, 4, 2, 3. Okay. All right. Just for additional practice, let's do BA. So BA here, I'm not even going to rewrite this. This would be, so 2, 3 transpose times 2, 1. So that would be 4, that would be 4 plus 7, or sorry, 4 plus 3, so that's 7 in the first slot. B, so then in the next slot, this is first row, second column. Right, so first row of B times second column of A, so or dotted with second column of A, so this would be 2 times minus 2 plus 3 times 0, so this would be minus 4. Okay, second row, first column, so this would be second row of B, dotted with first column of A, so this would be 4 times 2 plus 1 times 1, so that's 9. And then lastly, second row, second column, this would be second row of B times second column of A. So this would be 4 times minus 2 plus 0, so that's minus 8. Okay. And you can see those are very different matrices. Matrices, like vectors, the only possible way two matrices can be equal is if absolutely everything about them is equal, right? So component-wise. So for instance, two matrices are equal if and only if the 1, 1 component is equal to the 1, 1 component here, the 1, 2 component is equal to the 1, 2 component here, and so on. Okay, so just like vectors, the corresponding components have to be equal, okay, as real numbers. Okay, so that was our lengthy aside to go over this. This is important, though, because as it turns out, like I said, solving these differential equations, these systems, entirely reduces to a linear algebra question. There's a little bit of conceptual stuff, a little bit of theory, where we are, of course, going to use the fact that we are talking about a differential equation here. So there's obviously some things that pop into it that have nothing to do with linear algebra, because linear algebra does not concern itself with derivatives. Okay, but basically, with like 10% background from the differential equation side of things, the remaining 90% is a question of linear algebra. Okay, so going back here, rewriting this equation. So if A is A11, A12, A21, A22, right? Then what is A times X? Well, we can actually just do this dot product now. So this is A times the vector X. So what do I get? I get a single entry here in a vector. I'm going to rewrite it like this just so that you see. From now on, I won't do this. Okay, I'll just do it in one step. dx dt, what is that? That is d dt of this vector, right? x1 of t, x2 of t. Okay, and that is equal to A times X, which is A11, A12, A21, A22, times the vector X, which is X1 of t, X2 of t. Now, I'm going to do matrix multiplication here. Of course, matrix times vector works fine as long as the sizes match up. This is a 2 by 2. This is a 2 by 1, so the resulting thing should be a 2 by 1 column vector, right? So what is this? I only have two entries, the top and bottom here. So this would be, first entry would be I take A11, A12, that first row, and I transpose it and dot it with this column here. So this would be the vector that is A11, X1 plus A12, X2. And in the second entry, this would be A21, X1 plus A22, X2. But these two vectors are equal. Of course, ddt of x1 and x2 is just, I just take the derivative of each of these. All right, so it's the vector that contains the first derivative of these two things. So rewriting this, if I have two vectors are equal, that means each component in the vector is equal. So that leads me to what I was about to write, which was dx1 dt is equal to a11 x1 plus a12 x2, and dx2 dt is equal to a21 x1 plus a22 x2. There is what my system of equations looks like, okay, when I write it out like this. So let's do a specific example, right? So I want to write the system dx1 dt is equal to minus 4x1 plus x2, and dx2 dt is equal to, say, 5x2. So write the system as dx dt is equal to ax for some matrix A of constants. Okay, and so how to do this is I let x be the vector x1 of t, x2 of t. Right? Then what is A here? Just reading off our last line. A is going to be the matrix minus 4, 1, 0, 5. Right? And you can just check if that is the case. Then indeed what this is ddt of x1, x2 is equal to A, which is minus 4, 1, 0, 5, times the vector x1, x2. I suppress the notation here. Of course, x1 and x2 are both functions of t, but you'll frequently see the notation suppressed here just to keep everything more compact. Okay. And so, what is the idea here, maybe? Okay. Well, as I've already said, this is the exact type of equation that I'm going to be very interested in. Okay, this is going to be the main thing that I care about here. Okay. Now, what I want to do is ask the big question, right? How do I solve this equation generally? So how do I solve, I'll write this as star. How do I find a general solution of star? We are going to be using methods that are very, very similar to what we've done before. Especially they're conceptually similar since we're even going to be using the same language. And now, rather than this language just kind of evoking linear algebra and not explicitly like referencing matrices, that's what we're going to do now, because now we have explicitly matrices and vectors showing up. And when we say linear independence, that's a very specific meaning, and it is the same meaning we're used to from linear algebra, and so on. So this is the point. Now, how do I find a general solution of star? So this answer is going to be provided. So I should say there are multiple paths here to the general solution. Our main approach will rely on what is called Eigen methods. So our main approach to solving such systems comes from what are called Eigen methods. Now, if you have had 240, you will know exactly what is being referenced here when I use the word eigen, or the part of the word eigen. All right, so this is going to involve eigenvalues and eigenvectors of a matrix. Okay. Now, if you don't know what that is yet, don't worry. We are going to explicitly go over that. But this, it turns out, is not only the most convenient way of kind of going about this, it's also the way that, in a sense, gives us more info, or more readily usable info. Now, technically, I could cook up some problems where there would be methods that are not eigenmethods that would be better suited for the purpose, or maybe a little more convenient, depending on the info that you're given for the problem. But in general, from scratch, the eigenmethods approach is going to be, the one that is going to get you there with the least amount of hassle. And in this course, we're going to focus mostly on eigenmethod stuff. Okay, so I am going to do an example here, going a little backwards. Okay, so consider the system. So I'm not going to impose any initial conditions yet, but consider the system ddt of x1, x2 is equal to the matrix 3, 2, 2, 3 times x1, x2. So there's my A, right? So A here is 3, 2, 2, 3. Okay. Well, I want to check a vector that I'm going to call big X1 of t. So big X1 of t is the vector containing the functions e to the 5t, e to the 5t. Now, a simpler way of writing this technically would be as e to the 5t times the vector 1, 1. That is perfectly valid, but I'm going to take this for now. Let's check that x1 actually solves this system. Okay, so let's check that big X1 solves this system. Okay, well, big X1 of t is this vector of functions e to the 5t, e to the 5t. So if I let x1 and x2 both be e to the 5t, what do I get? So let's check. So here, this equation, of course, is the same as the system dx1 dt is equal to 3x1 plus 2x2, and dx2 dt is equal to 2x1 plus 3x2. Okay, but x1 of t, saying that this solves the system, is saying if I let x1 and x2 both be e to the 5t, that I should get what I want here. Let's just check to make sure that this works. So then the question is, what is d dt e to the 5t in either case? And this is 5 e to the 5t. Okay. Does that match up with 3x1 plus 2x2? Well, 3x1 is 3e to the 5t. 2x2 is 2e to the 5t. So this is 3e to the 5t plus 2e to the 5t, so that's 5e to the 5t. The first equation is true, but the question is, what about the second equation? So what's 2x1 plus 3x2? Well, that's 2e to the 5t plus 3e to the 5t. So that is 5e to the 5t. And so the second equation is the derivative of e to the 5t, which is 5e to the 5t, is equal to 2x1 plus 3x2, which is also 5e to the 5t. So both of these work. All right, and remember, solving a system of equations means you have to solve both of them simultaneously. It's not enough to just solve one at a time, right? That's not a solution to the system. So this indeed solves the system. Okay. Is that going to be enough? Am I going to be able to form a general solution from this? Well, while you think of that, let's do another check. Okay, so let's check that the following also solves the system. So let x2, so let big X2 of t be equal to the vector e to the t minus e to the t. Now, if we were writing this a little bit more conveniently, we could write this as e to the t times the vector 1 minus 1. You might say, why would I do that? Just like I did up here. It will become clear eventually. Hopefully by the end of tomorrow's lecture, I think I'll have covered enough that this will become clear. But the reason for this is it is going to be apparent once we put it in this form what we mean by talking about eigenmethods and where the eigenvalues and eigenvectors show up here, right? Some of you may have already picked this up. 5 and 1, it's going to turn out are eigenvalues for this matrix A. And eigenvectors associated to those eigenvalues are 1, 1, and 1 minus 1. Okay, so you can, if you already know about eigenvalues and eigenvectors, you feel free to verify that that's exactly how this works. Okay, if not, then just sit back and wait for me to get to that stuff later. So if here's big X sub 2, this is e to the t, e to the minus t here. This is e to the t times 1 minus 1. Yeah, I'm just going to use this. So I'm going to check that this is also a solution. So check that x2 of t also solves the system. Okay, so check that x2 of t also solves this system. Well, remember, this is what we're checking here is that dx1 dt is equal to 3x1 plus 2x2, and we're checking that dx2 dt is equal to 2x1 plus 3x2. Okay, and so just quickly here, so x1 and x2 in this context are the first and second components of this solution vector. So this would be checking that d of e to the t dt is going to match up with this. So let's see here. This is e to the t. I think we can do that derivative. But what is 3x1 plus 2x2? Well, that is 3e to the t minus 2e to the t, because x2 is minus e to the t. So this is 3e to the t minus 2e to the t, so this is just e to the t. So the first equation matches. The second equation is checking that dx2 dt, which is de to the minus t dt, of course that's just minus e to the t, and that has to be equal to 2x1 plus 3x2. So 2x1 plus 3x2 is going to be 2 times e to the t plus 3 times minus e to the t. So this is minus 3e to the t, okay, which is minus e to the t. So both of these equations are satisfied, and this is another solution. So I have found two vector valued functions here, right, that solve my system. And they're definitely different, right? So you can just compare them point-wise. They do not match up at all, right? So at t equals 0, for instance, this is at 1, 1, and this is at 1 minus 1, right? When t is equal to 1, this is at e to the 5, and this is at e minus e, right? So definitely just totally different things here, okay? So this, both of these solve the system. They're clearly different. The question is, how many times can I do this? Can I keep going? Could I find a big X sub 3 that made this, that also solved the system that was different than these two? The answer is no. I have enough here, and the reason I have enough is that I have 2 here. And you could have said, well, what about okay, maybe I'll be a little bit more technical here. What if I chose X sub 3 of t and said, okay, X sub 3 of t, I'm gonna pick that to be 2 e to the 5t, 2 e to the 5t. Does that solve this system, or this equation here, this system of equations? Does that solve it? It does, actually. You can check yourself. If you don't believe me, it definitely solves it. Okay, so you don't have to worry about that. In fact, I can actually combine these by adding them together, right? And that would also solve it. But this is called the principle of superposition, right? This is from the fact that this is a linear system, right? So also, if I let x sub 4 of t be like x1 plus x2, like the sum of those vectors, then this also solves it. So x sub 4 of t also solves it. Now, you probably see where I'm going with this, right? So, I found 2 legitimately distinct I'm using all kinds of euphemisms here. So, I found 2 definitely different solutions, x1 and x2, right? I'm using all kinds of euphemisms to avoid spilling the beans and saying exactly what it is. Like I said, a lot of you probably figured this out. x1, x2, these are different enough, right? Okay, so this is a solution, this is a solution. X sub 3 is technically different from both of these, but of course you see it's just a scalar multiple of x1. So I needed to find this before I could cook this up, right? And of course I could have used a different scalar multiple here. I could have used minus 5, I could have used 10 square root of pi times this, it would have been the same thing. So taking one of these and multiplying them by scalar gives me another solution. But this is not as different as these two are from each other, right? So similarly, if I take 2, x1 and x2, and I add them together, that is, again, technically a different solution, but it is not a solution that is different enough from these two, right? In fact, it was formed from those two. Okay. So, and if you wrote this out, right, if you wrote this sum out, then x sub 4 of t, because this might look, totally different enough for you. It's x sub 1 plus x sub 2, so this is e to the 5t plus e to the t in the first slot, and in the second slot, this is e to the 5t minus e to the t, right? So that is also not different enough from x1 and x2 because it's a linear combination of x1 and x2. In fact, it is true in general that if you have 2 solutions, you can form another solution by considering any linear combination of them. So I just chose 1 times x1 plus 1 times x2. I could have picked whatever. I could have picked 5 times x1 plus 3 times x2. That would have worked as well. This is the principle of superposition, right? This is the linearity fact that we used forever ago, back in chapter 2. That still works for systems, okay, for the exact same reason, algebraically, that it worked for us for higher order single equations, right? Okay, so clearly I've been beating around the bush here, and I've been avoiding mentioning what it is that makes these 2 solutions things I want to toss out, and what is really essential about the difference between x1 and x2, and that's that x1 and x2 are linearly independent. Okay, so it turns out that in this example, let me move my paper. So it turns out that in perfect analogy with what we did before when we first talked about general theory stuff in chapter 2, it turns out that x1 of t and x2 of t are linearly independent while x3 of t and x4 of t are not linearly independent of each other. I kind of phrase this in an awkward way. Really, it's that if I toss in x3 and x4, they're not linearly independent, relative to x1 and x2. As that's what is meant here. Like I said, it's phrased a little awkwardly. But somehow these form something essential. Okay. In fact, we've already used this terminology before. So it turns out that suppose we have an n by n matrix A, and we have the system dx dt is equal to ax. Okay. Then if I have a set of n linearly independent solutions to, I'll call this asterisk, to asterisk, we'll label those as x1 of t, x2 of t, all the way out to xn of t. Then x of t, which is defined to be c1 times x1 of t plus c2 times x2 of t, and so on, plus cn times xn of t, is a general solution of asterisk. Now, I haven't defined what linearly independent means technically, and I will soon enough. But if I have n linearly independent solutions, then this is said to be a general solution of my system. Okay. All right. So notice, first of all, the similarity between this statement and what we had for general nth order linear equations, right, with constant coefficients. So for those general nth order linear equations, the n thing, the thing that determined how many of these I needed to find a general solution, what was that? Where did that come from? That was the order of the equation, right? Well, here it's not the order of the equation because these are all first order systems, right? There's only one derivative showing up. It's the size of this matrix, which if I write A as an n by n matrix, what I really mean there is this isn't just saying A is an n by n matrix. You shouldn't think of it as A determines this. It's that this is a system of n equations, right? So this would be a system of n equations. That's what we mean by saying A is an n by n matrix. This is a system of n equations. So my solution vector has length n. Well, I shouldn't say it like that. My solution vector has n components. That's what I mean. Okay. All right. Okay. So this is a general solution. Let's just go back and see how that applies to the previous thing. So actually, I'll just rewrite it. So let's go back to our example. So we had dx dt was equal to 3, 2, 2, 3 times x1, x2. Okay, and so this gave me, so I found solutions. Big X1, which I wrote to be e to the 5t, e to the 5t. And big X2, which I wrote as e to the t minus e to the t. Okay. Now, suppose we knew that these were linearly independent. So suppose we knew that these were linearly independent. What then? Okay. Well, then by that fact that I just took away, right, then the general solution to this equation should be this linear combination of those things. So suppose we knew that these were linearly independent, then the general solution to this equation, I'll call it star, is x of t is c1 big X1 of t plus c2 big X2 of t is equal to, this is c1 times the vector e to the 5t e to the 5t plus c2 times the vector e to the t minus e to the t. There's nothing wrong with leaving it like this, but I'm just gonna, this is practice purely for doing algebra on vectors and matrices. So I can rewrite this, I can combine this as a vector, so this would be c1 e to the 5t plus c2 e to the t in the first slot. In the second slot, this would be c1 e to the 5t minus c2 e to the t. Now let's suppose that this had an initial condition imposed on it so that x of 0 is equal to 1 minus 1. Right? Well, then in order to find the unique solution guaranteed by this, and of course I didn't really go into this, I'll mention this a little bit tomorrow, but from the general theory for these types of systems, you get an existence and uniqueness theorem in the exact same way that we did in previous settings. So as long as you make as long as what you're dealing with is even remotely nice, you get existence and uniqueness, and so all of those same kinds of facts carry over into this setting. So if I plug in t equals 0 here, I impose this initial condition. So I have 1 minus 1 is equal to, I'm plugging in 0 here, so this is c1 plus c2. And plugging in 0 here, this is the c1 minus c2. And so I get the system c1 plus c2 is equal to 1, and c1 minus c2 is equal to minus 1, right? And if I just add these things together, right, adding these equations, I get that 2c1 is equal to 0. So c1 is equal to 0. Well, if c1 is equal to 0, then c2 is equal to 1. And so the resulting solution, the unique solution, would be x of t. Sorry, there should be a bar of this. So it would be x of t is equal to c1 is 0, c2 is 1. So this would just be e to the t minus e to the t. This would be my unique solution to that IVP. So you notice that, of course, you have to do some vector and matrix algebra here, but the actual process of imposing an initial condition is very similar to what you did in all the other examples of IVPs in this course, right? So nothing too crazy is going on there. Okay. So now the question becomes, how do I figure out that these are linearly independent? So we use the fact that we know that they're linearly independent to then say, okay, if I have a set of n, in this case, n is equal to 2. So if I have a set of 2 linearly independent solutions in this case, I can form the general solution like this, and that is the general form a solution must take. It can't take any other form, right? Any other distinct form. It has to be of that form. How do I know that these are linearly independent? This involves, as you might expect, a Wronskian, okay, which is, of course, itself a determinant. So let's define a couple of things here, okay? So let's define the Wronskian, right? So definition of Wronskian. Now, given a set of n solutions to dx dt is equal to ax, where x is the solution vector that has n components. So this is a system of n equations. A is an n by n matrix of real numbers. So given a set of n solutions to this equation here, so this is homogeneous, constant coefficient, first order linear system, right? So given a set of n solutions to this, the Wronskian, so we'll call the set maybe x1 of t, x2 of t. I want to draw attention to this. This is kind of bad notation, but we'll alleviate this a little bit when we just purely restrict ourselves to the n equals 2 case, so that this doesn't really come up. But notice that these component functions I've labeled as x1, x2, xn, but also these vector valued functions I've labeled as x1, x2. These, of course, have the bar over them to indicate that they're vectors, whereas these are scalar valued functions. So these are not the same objects as these, right? And I know that's a little bit confusing, right? So technically, right, this would have n components that would match, that would be these. This would also have n components that would be different in some way, blah, blah, blah. That's how this would work. So given a set of n solutions to this, if I write them out, here they are. Their Wronskian is the following. And this is very similar to the Wronskian that we defined back all that time ago. This is, so their Wronskian is simply, I'll write it in the same notation. This is the Wronskian of x1, x2, and so on, all the way out to xn of t. What is this thing? This is the determinant of the matrix whose columns are x1 of t, x2 of t, and so on. So maybe I should specify that. This is the matrix whose ith column is x sub I of t. All right, so here is my definition of Wronskian. Okay, so this is my definition of Wronskian. Here is my definition of linearly independent. Okay, so this how should I say this? So I'm not even going to go through the process of writing out Abel's theorem. But basically what Abel's theorem allows you to do is say that if the Wronskian is non-zero somewhere, then it's non-zero everywhere, basically, on the domain. If it's zero somewhere, then basically it's zero everywhere. And so what this means is that for the Wronskian, you don't actually have to work too hard to show that it's zero or non-zero. It's not going to be something you have to think about too much. So once you compute this determinant, it's basically going to be very easy to see whether the thing is 0 or not. So x sub 1 t and x sub 2 of t and so on all the way out to x of n of t, this whole collection of n solutions is said to be linearly independent if the Wronskian is non-zero. Again, by that I just said in my preceding comments, this is not going to be too hard to show one way or the other, because if it's 0 anywhere, it's basically going to be 0 everywhere, and if it's non-zero somewhere, it's going to be non-zero everywhere. So anyway, in this case, we say that they form a fundamental solution set. This is the same terminology we used previously. So they form a fundamental solution set for this equation. I'll call it star or asterisk. So they form a fundamental solution set for star. Okay. Now, in this case, is going to have associated to it a couple more objects of interest that I'll get to starting in tomorrow's lecture. But for now, what I wanted to talk about is the following. What I wanted to talk about is going back to this previous example where the equation or the system of equation in questions was this linear system that we saw earlier. So here it is. So A is 3, 2, 2, 3. Here's my system. We already saw that there were two nice families of solutions. So one was what we called big X sub 1, so it's e to the 5t in each slot, and big X sub 2, was e to the t minus e to the t. So let's compute their Wronskian. We already saw that they solved the equation, so then it makes sense to compute the Wronskian of these things. So what is this? This is the determinant of the matrix whose columns are x1 and x2. So this is the determinant of the matrix e to the 5t, e to the 5t, e to the t, minus e to the t. Okay. All right. We're going to see that this matrix has a special name, but let's compute this determinant. So computing this determinant, what do I get? I would get e to the 5t times minus e to the t minus e to the 5t times e to the t. And so this would be minus e to the 6t minus e to the 6t. So this is minus 2 e to the 6t, and that is not 0 everywhere, right? And so x1 and x2 are linearly independent. They form a fundamental solution set, right? So x1 of t and x2 of t form a fundamental solution set. Of course, the thing that we get immediately out of that is a general solution is x of t. So a general solution to this differential system is c1 x1 of t plus c2 x2 of t for arbitrary constants c1 and c2. This matrix is called the fundamental matrix. So this is called the fundamental matrix of the equation. Let me write out what the fundamental matrix is. So what we just showed here with this Wronskian is that the determinant of the fundamental matrix is non-zero everywhere. So that is showing in linear algebra terms that that fundamental matrix is invertible. I'll do a brief review of what it means for a matrix to be invertible now that we've had some practice multiplying matrices and it's more clear. I'll do that some next time or later when we need it. But the definition is if x1 of t to xn of t form a fundamental solution set, for this equation that I keep rewriting, dx dt is equal to ax, then C of t, which is the matrix that has x1 to xn as its columns, is called the fundamental matrix. So this is the fundamental matrix for this equation. So again, going back to our example, if we use the same example as before, the fundamental matrix C of t was e to the 5t, e to the 5t in the first column, and e to the t minus e to the t in the second column. We're going to see tomorrow that there is a really, really nice characterization of solutions to this stuff in terms of the fundamental matrix. This is going to tie into something called the matrix exponential. Okay. And the matrix exponential is going to be one of our approaches to talking about these solutions. And there are going to be multiple ways of finding matrix exponentials. But the easiest way in general for us is going to be through eigenmethods. Okay, so that's where we're going to start tomorrow. By the end of this week, we are definitely going to have a good chunk of the conceptual stuff of the chapter out of the way. We're basically going to be able to focus on a bunch of examples, and then we're going to be able to do a bunch with what comes next. This analysis on both what are called integral and non-integral methods. We'll talk extensively about that stuff. And then that will be the course. So anyway, that's all for today. So I will catch you all tomorrow at the normal time. Hopefully, it seems like all of my issues have been completely sorted. So hopefully there won't be any more tech issues for the remainder of the course. But anyway, that is it. So I will see you all then.